Hey there everyone, my name is Ryan Schul. Welcome to my data science channel. And today's project, I want to look at customer segmentation, and we're going to use Python, of course. Now, I actually made up this data. I looked in several sources. I couldn't really find what I was looking for. I wanted something just with basic gender information, age, annual income, spending score. That's important. Profession, some labels like this, work experience, family size. I found like some of these features, but not all together. So I just ended up creating 2,000 records using Python's random number generator over here. That helps out a lot, right? So we have gender, age, annual income, spending score, work experience, family size, and so on and so forth. So when I run this out, you can see it creates the data for us dynamically. Very nice. I like that. Then we can get some basic statistics on the data just to understand what some of the mins, maxes are. We get standard deviation, top 25%, top 75%. In terms of the age, right? You just correspond the value over here or the label over here on the left with the column heading on the top over here to get everything that you need. Now we can move on and create some dummies for gender and profession. Okay, so in the machine learning world, computers don't understand what languages. They don't understand sentences and words and label data and things like this. Now we can make them understand it, and there's ways to do that, but we have to encode the data before the machine is even going to consider looking at these things, right? It doesn't know what an engineer is. It doesn't know what the entertainment sector is. It doesn't know executive, female or male. It doesn't know these things, right? But we can encode these using a couple different techniques here. I'm using one-hot encoding to get dummy data and create a 0 or 1 for just get dummy data. It's encoded data. It's not one-hot encoding. Oh wait, it is actually. This is, yeah. So we did get the dummy data here, okay? And this is everything is encoded at this point. So again, we're taking everything that's not numeric and converting that into a numeric representation using this encoder. Then we can go ahead and do our analysis. But if we just put in male and female and accountants and what else do we have here? Engineer, like the computer has no idea what those things are, right? Once it's encoded, it can figure it out and it can learn from that. But until we encode it, the computer just isn't going to know. So because this is customer segmentation, I'm going to do some basic and a few not so basic clustering techniques. I'm going to use k-means clustering. I like to start with this one. This is probably the simplest one to set up and understand, but it does have its limitations. Because of its simplicity, it tends to really work well with data that's round or has kind of a round shape. If your data is long and stretched out, vertical or horizontal, or has a very complex pattern, I guess, k-means is probably not the best solution, but I'm going to take you through it and show you why it could work, but it's not really going to work in this case, okay? So I went ahead and plotted a elbow chart over here where the bend is the biggest in the elbow chart. That tends to be the optimal number of clusters. So I'm going to pick n. I'm going to look for the bend first. Okay, I did this 20 times. I ran through 20 iterations of clustering. The bend is at 7, so I set that as a label so I can get a visual clue over here where the bend is occurring and how many clusters I'm going to need. Okay, so I just discovered this technique. I think that's pretty nice, and I'm going to use that down here. Okay, so we have to set the number of clusters that we think ideal based on this clustering curve. This is what this algorithm is coming up with, right? The k-means clustering says 7, so I'm going to use 7. But we'll see in just a minute that there's actually a couple ways to do clustering. There's actually about, I think, 8 or 9. We're going to see a few different techniques. And for some of these, they actually determine the optimal number of clusters for you. You don't tell them how many clusters to pick. The tool actually tells you, or the model tells you how many clusters. So this is what we get with the k-means. It's 3-dimensional. I can zoom in, zoom out, spin this thing around, and we have the 7 different segments. We start with 0, and it goes up to 6 because Python is 0-based. So if it looks a little weird, like we're missing one or got cut off, it's really starting with 0 and going to 6. So there's our 7 clusters, and we have the details here: doctor, lawyer, female, and the cluster that they fall into. But is this really helping us? I don't think this really helps, right? You have to do these exercises to see how things shake out. But right now, I don't see any defined clusters there whatsoever. So we have to try a few different techniques to manipulate the data and to manage the data a little bit differently and try to figure out how these clusters are really going to form together. And then that's going to help us with our customer segmentation. Okay. So we have data set with age, income, spending score, so on and so forth. These features exist in 5-dimensional space. So here's 5, 1, 2, 3, 4, and 5. But can we represent 5-dimensional space in a 2 or 3-dimensional space? We cannot, right? Here's the 3-dimensional chart, and that is as many as we can get. You can argue this is actually 4-dimensional because we have different colors for the clusters. So this is probably better classified as a 4-dimensional chart. Okay, so the 4 dimensions would be annual income, age, spending score, and then the color for each label in the cluster. But even with 4, that's hard to do. Can we do 5? We actually can, because we can add shapes too. We're using only circles now. If like we want to show males as one cluster and females as another cluster, we can add a shape like a triangle and a circle. We could do that, or a triangle, a square, or something like that. But I don't think that's really going to help solve the problem, so we're not going to even go down that path. So if I do a PCA, principal component analysis, I can take all of these features, which were spread out across 5 different features, right, and capture the first 2. These are the principal components that really show most of the patterns in the data. Otherwise, everything gets mixed together, it gets jammed up into space over here, right? But we can actually tell what the principal components are and just tease out these 2 in this next chart, and we can already see that this is one cluster right here, right? So that is pretty well defined. And this is cluster segment number 1. But we still have some issues down here with 2s and 5s blending together. I saw some 4s. 3 looks kind of okay, but it kind of blends. And this is segment 6 over here. So that is cluster number 6, but it just gets too busy in here. And I don't like it very much. It's not helping us really solve the problem. So we're going to continue on and try a couple more different techniques. So remember when I said k-means can be very helpful and useful in some circumstances, but that's basically if the data is somewhat spherical or somewhat maybe egg-shaped or oval or something like that. If it has all these complex patterns interwoven together, k-means is not really going to help us solve the problem. But we do have a few more clustering techniques that we can try out. One is called DBSCAN. It's density-based clustering that helps find, it helps to deal with noise, right? There's a lot of noise in this chart right here. If you look in the middle, this is very noisy. It's very busy. We don't have cleanly defined and separate clusters, right? So there's a lot of noise. DBSCAN is good at dealing with that noise and teasing out the density of those clusters, and then we can plot the results and see what those are. And I'm trying another one, a GMM model. This is a probabilistic model that assumes that data comes from multiple overlapping distributions. That's what this looks like to me. It looks like there's a lot of business, a lot of overlap right here, and k-means just can't deal with it, right? It can't handle it. So we're going to try a couple different techniques, and again, run the PCA test, principal component analysis, and we're going to look at the DBSCAN segment. Okay, so Control Enter to run the cell. So we do get a little bit of overlap here, but the clusters are still very much on top of each other. They're very busy. It's all scrambled together, so it's not super helpful. But this is interesting. The DBSCAN actually picked the number of clusters for, so it says there's close to about 70. I see segment 1, 2, 3, and so on and so forth. You can see by the color chart, it's picking about 70 different clusters. And I didn't define that anywhere in the code, right? I don't have that here in the chart. I don't have that in the DBSCAN. Okay, so that's interesting. With the k-means, you have to define the number of clusters. With DBSCAN, the model tells you the optimal number of clusters, right? It's a very different technique where you're looking for the density of where these data points sit on the map, right? On the plot. Sorry, on the plot. So let's try again PCA with GMM segmented. Okay, so this is Gaussian Mixture Model. So again, kind of like the DBSCAN, it kind of handled these guys over here. They segmented those pretty well. Okay, so I'm not concerned about those. The yellow and orange kind of blend together, and it runs with the pink in the background here, or magenta, whatever that is. And that seems like some of these down here, some of these segments, these are clusters, kind of overlap too. So the GMM really isn't solving the problem either. So now we've tried 3 different clustering techniques, k-means, right, the DBSCAN and the GMM, and we're still coming up short, right? So how can we cleanly define these clusters? I have some notes over here about what these things do. K-means is good, but the assumes spherical clusters. DBSCAN is poor in this case, and in a lot of cases. But if the cluster arrangement is highly dense and you have just a very small concentration, maybe you can think of fraud, credit card fraud or something like that, or wire fraud if somebody's trying to send money to somebody using a bank. That would be probably easily detected with DBSCAN, but not with some of these other clustering techniques. GMM is actually giving us clean interpretable segmentation, but it's still kind of busy in the middle, and I think we can do a little bit better. So we're going to try another technique. Okay, so let's move on. We are going to scale all the data. When you're working with cluster data, you always want to scale it, because if you have outliers, very high values or very low values, it's going to skew things and kind of mess up your clustering. So we want to take everything and standardize it. We're going to use a standard scaler. Once everything is scaled, everything is somewhat relative to everything else. So you don't have these extreme high outliers, extreme low outliers, or any kind of outliers. So you don't fundamentally change your data. You just change how the data is scaled. So the high is still going to be high, but it's not going to be 20 times higher, and the low is going to be lower. It's not going to be 1/10 of what the average of the population is going to be. Everything is going to be on the same scale. And I believe for this one, it goes from -1 to 1. Let me see, scaling range, or 0 to 1. I forgot. There's 2 ways to do this. SCALI. No, I think -1 to 1. Is that how it's working? Just search the not matching documents. Scalar. Well, it doesn't even return any. I haven't seen that in a long time. I think we just broke Google. Okay, but I'd have to look into that. I think it goes from either -1 to +1. That's the range of scale, or it goes from 0 to 1. I forgot which is which, because there's 2 ways to do this. Right? But I'll look into that, and I'll add that to my notes at the end. So, okay, so we're going to try a different technique again. PCA. So we're going to do the principal component analysis. We're going to use the MEX cluster for the color. Okay, and we are going to plot this, right? We just created the MEX cluster over here. Control Enter. Yes, and we can plot it. I think I just hit that. I'm going to do it again just to make sure. So now we have a different distribution of the data. It's just transforming the scale of the data. Oh, here it is. It goes from -3 to +3 in this case. Okay, I think, though, you can set those ranges, but you can see how everything is on the same relative scale on the x-axis. If we go over here, back to the k-means. No, it still had the -3 to positive. Okay, I'd have to look into that too. Okay, though I have a little bit of homework to do. I have a couple open items because I didn't put that in my notes, and I didn't notice that until just now. But okay, we're fine. We're fine. We'll get through this. So we now have the same kind of cluster arrangement that we saw before in the other examples, right? And this doesn't have to be a specific cluster or a specific cluster number. It just has to be clustered with its peers. Okay, so this could be cluster number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, cluster 100. I don't care. I just want everything that has the same relative dense shape, or the same relative pattern, or the same relative scale as all its peers to be clustered together. That's the objective here. Okay, it's not the color. It is only, and this was set to 2. Didn't we say 7 was the ideal? Let me change that. I think 7 was ideal. Oh wait, it actually comes from here, right? Control Enter. We have to do the analysis first. Okay, then the plot. Okay, now we get 7. Okay, and again, it goes from 0 to 6, with 0 being the first, and 7 is essentially 6, right? So again, we still have some cluster definition, but there's still way too much overlap and way too much busyness in here to be extremely valuable for us. So we have to try another technique. This is t-SNE, and with the t-SNE, it's really good at teasing out all the interactions of this very complex data set. You can see how complex it is, and really spreading it out. Again, using a method similar to PCA, we're looking at all the principal components and what has the most impact on these clusters. And finally, number of components, I want this to be 7. Finally, we see some well-defined clusters. Oh, did I go too high for that? Okay, I'll tone it down a little bit. Let me try this. Oh, wait, maybe it's 2 because there's only DF1 and DF2, t-SNE1 and t-SNE2. Okay. Yeah, I was thinking that was a cluster input variable. No, it has nothing to do with that. It's looking at these 2 variables right here. Okay. So this has to be set to 2 because that's the number of components that we're testing. And you'll see when this finishes, it has very nice segmented and very well-defined clusters. Now we know who we can target, right? We made that customer segmentation, and we know which customers fall into which buckets or which clusters, right? So these 2 are actually the same cluster, cluster number 6. These 2 are actually separated, but these belong to the same cluster, so we can combine those. And this is cluster 4 and cluster 4, but everything is parsed out and separated, so it's very well defined. And by the way, I don't think I even mentioned it before, but just if you're wondering where all this clustering stuff is coming from in the data, we actually set that when we run each of these. So we have the clustering right here, k-means. We set the number of clusters to be 7, and then we take the results of this x variable. Remember, I know I said this, but I think I forgot one thing. We have all of these as the x variable. So the x is the independent variable that we're working with. And once those are converted to numerics, we can test for that variable. And that's how we get all these clusters. And we take the cluster and assign it to a new column in the data frame. So we have df.segment. Okay, there's df.segment. So we take the original data frame, which came in like that. We did the k-means and got that column. And it's exactly the same for DBSCAN and for GMM. So if we go down here, DBSCAN goes over here, DBSCAN segment, GMM goes to the same data frame and just assigns a new column. So you have segment, and then DBSCAN, and then GMM segment. And then when you look at the data frame, after this is all done, I could just go down here and show the data frame. I'll do it here and then just remove it, display. df.head. Okay, so here was the k-means, and then we had DBSCAN, GMM, MEX cluster, and then t-SNE1 and t-SNE2. So that's the whole point. You just take all these clustering methods and just keep on assigning it to the same column or to a new column in the data frame. So all these rows will match up, right? And you know where this person is going to in this cluster. This is cluster 1, right? DBSCAN says 0, GMM says 1, and MEX cluster says cluster 4. That's how we were assigning all these data points to the data frame. Okay, so just so you're aware of that. Okay, so I think I missed that point the first time around. So we get very tight and distinct islands of clusters. t-SNE is nonlinear, and it's great for visualizing high-dimensional structured, or in this case, non-structured data. Non-structured. Well, this is both structured and non-structured. It's more structured because it's in the data frame. So high-dimensional structured data, k-means assumes equal size. Spherical clusters, we definitely don't have that. So you need a little more horsepower. You need a little bit more help with this lift. So that's t-SNE comes in really nice. So for visual separation and interactivity, k-means plus t-SNE is great. For probability targeting and advanced modeling, you could use GMM. And for marketing, A/B testing, either one is fine. Okay, k-means is simpler. GMM is a little bit more complex, but sometimes you need complexity, like we saw in this case right here, over simplicity. Okay, so if I go ahead, how much will a customer spend? I think I can delete that. That's just testing some ideas. So now we want to take all of this knowledge and say, how much is the customer going to spend at our store? Okay, so let me refresh this. So we've done all the data analysis. Feature columns is not defined. Oh, let me look into this. Feature columns. New customer. Oh, so let me look into this. I was playing around with the code. I must have tripped over something. Must have made a mistake here because I erased something, unless it came from back there, because I did delete that. Feature columns. Did I have that over there? Oh, okay. I was playing with that. I do need that. Okay. Yeah, let me end that back up. Okay, that was a big mistake. That's fine. We're fine. DFO. I don't need that. I need that because I already have that one. Okay. So I think this will work. Let me test it. Okay, so that's the answer. That's the question we're trying to answer. So we have all the clustering, we have all the analysis done, business analysis or just fundamental analysis, whatever you want to call it. We have the more advanced clustering complete. Now we want to know how much is the customer potentially going to spend in our store. Remember, we had some data that was very useful at the beginning. I showcased this. The spend score from 1 up to 100. So 100 is a high roller. They spend a lot. This guy probably spends $1. maybe even less. Can you even buy anything for less than $1 today? I don't know. But on a relative basis, the 100 people with 100 scores are going to spend a lot more, and the people closer to 1 are going to spend a lot less. So based on that information and the gender, age group, annual income, the profession, the average ability to spend in the store, we can make assumptions about which customers are going to spend the most money. So again, we take all this, put this into the model. We're looking at numbers. So we're getting all the number features from the data frame. We're scaling it. So we're taking the scale. Again, to handle outliers, whenever you're working with any kind of clustering, I don't care if it's k-means, DBSCAN, GMM, what else is there? There's a few others. Hierarchical clustering. There's one, agglomerative clustering. I've used that before in the past. So you always want to scale your data so you're dealing with the same relative store of data points from the mean. If you have extreme outliers, it's going to drag the cluster over to the side. If you have extreme low outliers, it's going to drag some over there. But when you scale everything and fit it on the same relative basis, the clustering algorithm will perform much better than if you don't do that scaling, okay? So I did the training testing, new customer. This is random forest regressor. So that is the model we're looking at. SK, I'm just looking, where is this thing coming from? Because I don't see it now. Okay, so random forest model. That is the model. We're fitting the model right here. Then we're making predictions, right? So based on all of these inputs, gender, male. This is 1 if male, 0 if female, profession, professional healthcare, 1, annual income 55,000, age 50, work experience 5 years, family size 3. With these variables, we can make a prediction of how much this customer is going to spend, and this individual that fits this profile is going to spend about $45. Now, if you have changes that you need to make, right? If a new person comes in, oops, I just had that. If I get 3,500 and just change some of the parameters here, work experience could be 12 years, then that person is going to spend more or less. I don't know offhand. We have to run the model and test it. But this is why we trained the model. We trained it right above. 45.99. Let me change a couple more things. If this goes up quite a bit to 95,000 and work experience 22 years, how much is this guy going to spend? And it doesn't always have to be you make more, you spend more, but based on the data that we fed into the model, that one happens to be the same. That's a little bit weird, but that's fine. Once the model is trained and tested and you feed that into the model, it's going to make predictions into the future based on these assumptions that you make over here, okay? So let me feed in one more and see what the output is over here. 45.99. That sounds a little bit weird because we got that a couple of times. Let me look into that. Something might not be refreshing. I don't see anything that seems to be off here. But let me look into that. If there's a bug, I'll fix it. It could be the same. We only have 2,000 records in the data set, so some of these are going to line pretty well, but this is kind of precise too. We have 2 decimal places over here after the 2 places of precision after the decimal. So let me look into that. I'll fix that. If something is not refreshing, I'll force that to work. And then the last thing we're going to do over here is take all the information. We did the regular analysis, we did the clustering, we did the model testing and prediction over here. Now, who should I market to? Because everybody has limited time, you have limited budget, you have limited resources, right? Who of all these people should you be marketing to based on the annual income of the person and the spending score? And we're going to look at the mixed cluster. That's why we did the analysis over here. Remember, we did the mixed clustering Then we could do a control F. That's just easier for me. Control F. Mixed cluster is where? Right here. Okay, so we actually assigned it above that, right? So yes, it came from this mixed cluster. So this is using what I think the k-means and the t-scores, right? I think that's what that was. So based on this mixed cluster, which you can see over here, right here, okay? So again, we take that variable, the output from the clustering tool, and assign that to the data frame. And based on that, we are going to make a prediction of who, not really a prediction, but like answer the question, who should I market to? So if you take your top couple of customers, these are the high value customers, high value income, low spend segments. The low spenders are underperforming with their peers, right, in different clusters where you have the high spend people. But let me go ahead and run this, control enter. And we are sorting by spend score from 100 down to 0. That's how we get this. So we have this person, that's who we should be marketing to, or that demographic. So males that are 64 years old that have around 90,000 in income, these people are going to spend a lot more in our store based on all the analysis that we did. So that is one group that we should target. Females are aged about 29, making 50,000 a year. That's who we should target, okay? This is in descending order. Okay, sort by spend 1 to 100, ascending equals false. And this, if you want the top 5, this is the top 5. By default, the dot head gives you the top 5, right? If you get the tail, they would give you the bottom 5, right? Tail, I'll just do that, show you. Control enter. Okay, so these are the bottom 5. So we don't want to spend any money on advertising to this demographic or this one or this one or this one, because they just don't spend a whole lot in the store. 31, this guy kind of spends a lot, but why is he falling off? Different cluster apparently. But again, we're sorting by spend score, and we're looking at the spend and the annual income. I think that's why, like this person or this group would tend to spend a little bit more, but their income is kind of lower. And this group has lower income. This group has low income and low spend score. And these guys would have the higher incomes, right? Although this spend score is kind of low. That one looks a little bit weird, but these others make sense to me. Okay, so that's it. That demographic, and that demographic would be the top 3 for you to target with your advertising spend and your marketing budgets. Okay, so that is it. Customer segmentation using Python, and then we can actually use the model that we trained, which was the random forest model. If I go back here, I'll show you. We just saw that. So if you go back here, random forest model, we can actually make predictions about the probability of someone spending in the store. Okay, so we have the top spenders over here, sorted in descending order by spend score, right? And that comes from a combination of mixed cluster and spending score plus annual income. And now we're using the models to make predictions. And the model says the spend predict is about 88%, 88%, 87%. So again, we are sorting in descending order. If I did ascending equals true, then we're going the opposite way, right? That's how that works. But we're going descending because I want to see the top spenders over here, and you can see this is 13.01% likelihood of spending. This is 14. We don't care about these guys, right? We want the high spenders, so we want ascending equals false. We get the descending. There is no descending per se. And then you see the high numbers 88, 88, 88, 87, and 87. And if you want to create a cluster of MVPs, the most valuable person, or most valuable player, or most valuable customer, this could be an MVC. This could be MVC. You can look at the means and accounts, sort values again by mean in descending order. So ascending is set to false based on the spending score and the mixed cluster. The top customers, top 5 would be right here. And again, we don't have people's names. This is anonymous data. I mean, I actually made up the data. So, but we don't need people's names. We just need to know the demographic. Males, 64. we should spend money and spend time trying to find these people. Female 29, male 79, male 25, male 38. And this is a spending prediction. 73% likely, 65, 54, 20, and 21. And that's it, guys. That's how you do it. Customer segmentation using Python. Okay, so hopefully this was interesting and informative. Hopefully I was able to drop some knowledge and help you guys out. And I like doing these videos too. It helps me. And if I can help you, then that's win-win. Okay, so I'm going to wrap it up and I'll see you guys in the next one. Bye.